Alright, today we're going to work on simplifying radicals or simplifying square roots. We're going to kind of start with this practice problem. So the square root of 25 is 5, the square root of 4 is 2, multiply those together and get the answer of 10. Square root of 100 is also 10. So I gave these two problems for a reason, because there is a relationship between what we started with and there's a reason that we got the same answer. If I have this and I have two numbers under a square root or the radical sign, I can multiply them together and then take the square root. So I really could have done 25 times 4 is 100 and the square root of 100 is 10. So when we have the new rule, that's kind of what I would like us to know, that if I have the square root of A times the square root of B, that's the same as the square root of A times B. And it works in reverse order. So if I could separate it into two separate things and it would work as well. Okay, perfect squares. These are ones that we know and we have done before. I'm guessing most of you are like, oh, well, the square root of 49 is 7. And the reason being is if I make my factor trees, and I do 7 times 7, we get 7 squared is 49, and a square root and a square kind of undo each other, so my answer is 7. Or you can think of it as we look for what is there two of. There's 2 7s, so there's a group of those. Square root kind of undoes that grouping and says, how many do I have in that? So square root of 10, well, we could think that we know 10 times 10 is that, which is the same as saying 10 squared. So the square root of 10 squared is just 10. Again, I know you guys already know how to do this. You're like, oh, I know it's 10. But there's a basic understanding of kind of a square root and a square undo each other and cancel each other out. That's what we're trying to look for. So if I'm asked to do this one and I don't have a calculator, that's kind of where that's icky and we say, ugh, that's a lot of work. So I'm going to start by making my factor tree, and I'm going to divide both of those by 2, or divide that by 2, and I get 288. 288 divided by 2 is 144. 144 is 12 and 12. Now right here, if I look at this, I actually kind of see two groups here. If I'm going to split this up and kind of think back to up here, I could say that the square root of 576 is the same thing as the square root of 2 squared, I got that right there, times 12 squared. Now, if I do that, those squared and square roots kind of cancel each other out, so I'm left with 2 times 12, so the answer is 24. So again, because this is where it's starting to get kind of tricky, is we're looking, what do I have two of the same number that are multiplied to get that? So I got 2 times 2, so 2 squared. 12 times 12, so 12 squared. The square root undoes both of those, so I have 2 times 12 is 24. Okay. Square root of x squared. Well, a square root and a square undo each other, so that's just x. You could also look at it as this is x times x. That's where I have a group of 2 of the same thing, so I fill it out as 1x. Okay. Well, I kind of think of how can I write this with a squared. Do you agree that that is x squared squared is x to the 4th? Because you multiply. So this and this cancel out, and I'm left with just x squared, because that cancels. So the same thing here. How can I rewrite this as something to the 2nd power or squared? Well, I know x to the 3rd squared is x to the 6th. Y squared squared is y to the 4th. Square root those, that cancels out that square root and that, so I'm left with x to the 3rd, y squared. And another quick little thing you could see is really when I square root an exponent, you're taking half of it. So that's kind of where that comes from. Okay, now is where we get into our non-perfect squares. These are ones that don't have perfect square roots, because the square root of 50, if I type in my calculator, is going to be a decimal. So we're looking for in there for something that is a perfect square. So I know, like, how can I multiply to get 50 that uses one of my perfect squares? Perfect squares are 1, 4, 9, 16, 25. Again, I'm getting those by just doing 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. So this is kind of my list of perfect squares, and I'm going to look and say, are there any of these that fit in there nicely? 39, 64, dot, dot, dot. Well, I know 25 times 2 is 50. So I think, oh, well, I'm going to split this up backwards of what we did in the practice. Square root of 25 times square root of 2 is the same as square root of 50. Well, I know the square root of 25 is 5. Square root of 2 I don't know, so I'm going to just leave it like that. that is a simplified radical. Okay, square root of 32. Well, I know that, let's see, 1 doesn't fit in there. 4 does, but I'm going to see if there's anything higher. 9 doesn't, 16 does. So 16 and 2. I'm going to square root 16, which is 4, times the square root of 2. All right, 500. Well, 500 could be 5 and 100, those square roots. I don't know the square root of 5, but I know the square root of 100 is 10, so it's 10 times the square root of 5. This one is huge. So I'm going to really just kind of pull out, oh my goodness, what do I have here? So I know 100 fits in there. So it'd be 100 times 18. And then, is there some more square roots, perfect squares, that fit into 18? Well, that would be 9 and 2. And I take the square roots of the one I know. I know the square root of 100 is 10, the square root of 9 is 3, and the square root of 2 I don't know. And then we multiply those together. So it would be 30 times the square root of 2. Now is where we start getting in our exponents. These are a little bit trickier because there's not like those perfect squares that we know. But if you go back to up here, we kind of set our practice as just dividing by 2. The square root of x to the 6 is just dividing by 2, x to the 3rd. 4 divided by 2 is 2. So here I say, well, 3 divided by 2 is a decimal, so that doesn't work. So I kind of break it into ones that can be divided by 2. So I say the square root of x squared and the square root of x. That would become square root of x to the 3rd. Then I take the square roots of the ones I know. Square root of x squared is x. I have no clue what the square root of x is, so I leave it just like that. Here, I really just look for even numbers because I'm looking for something that can be divided by 2 nicely. So this is x to the 6th times the square root of x. Square root of x to the 6th, I just use that idea of it's really the exponent divided by 2. So it's x to the 3rd, square root of x. All right, this I kind of have a bunch of groups. I'm looking for this to be an even number, so I write x to the 4th. I still have one x left over. Y to the 4th is even, so I'm going to keep it what it is. Think of our idea of dividing by 2, so that's x squared. Then I kind of like to always take the ones I can do to get like outside, or the ones that I can actually square root and put those together. Y to the 4th, divide that by 2, so y squared, and I have that lonely little x by himself. Okay, this one we're going to do kind of 3 different groups. So I look at 20 and I say, what is a perfect square that goes into there? What can I multiply? And I've got 4, the square root of 4 times the square root of 5. X to the 5th, I'm going to change that to x to the 4th times x. And y to the 11th, I'm going to change y to the 10th and y. Now I'm going to take the ones that I actually know the square root of. The square root of 4 is 2. Square root of x to the 4th is x squared. Square root of y to the 10th is y to the 5th. And then I'm left with all those, so they're just going to all go under the radical sign.